All right, this is problem 541. An ideal gas at 2500 kilopascals is throttled adiabatically to 150 kilopascals at a rate of 20 moles per second. Determine the rate of entropy generation and lost work if the surroundings are at 300 Kelvin. And so this is a throttling process. The throttling process is discussed on page 88, and I think we forgot to mention that as we went through chapter 3, I believe it was. But a throttling process is where you throttle something or where you pass a fluid through a partially open valve. And so there's different kinds of valves, like a butterfly valve or a ball valve, or sometimes even something just like a porous material that just effectively forms a valve, or an orifice plate where you have an opening through here. But this is basically a throttling process where what you're doing is you're reducing the pressure. The energy balance, and there's an example problem on page 88 that goes through this. You can do an energy balance on this process. The energy balance is basically just there's no work being done. And if you are assuming that it's adiabatic, there's no heat, it's steady state, the energy balance is just delta H is equal to 0. Or the enthalpy coming in is equal to the enthalpy going out for your stream. And so we have this little valve here that we can open, P1, finally doing something kilopascals, 2500 kilopascals. Were we given temperature? Nope, we weren't given temperature. P2 is 150 kilopascals. Mass flow rate or mole flow rate in dot 20 moles per second. And we want to find entropy generation and lost work. Surroundings, T surroundings are 300 Kelvin. Oops, 300 Kelvin. All right, so that's our problem. Got a little schematic here for what it's worth. Partially open valve. We want to find SGen and lost work. This is an open system, right? It's open system, steady state. Adiabatic means it's perfectly insulated. There's no heat loss, right? There's no heat loss. So one of the questions, why aren't we given a temperature? We aren't given a temperature here. The answer partially lies in this energy balance from the first law, energy balance, which says H in is equal to H out, or delta H is equal to 0. This is an ideal gas. If delta H is equal to 0, then what has to be true? Well, remember, delta H is equal to integral Cp dt, T1 to T2. For that to Cp has to be positive, right? That can't be 0. What ends up happening? This is Cp T2 minus T1. The only way this is true is if T2 is equal to T1. So the temperature of our fluid upstream of the valve is the same as the temperature of our fluid downstream of the valve, and that makes sense. And we will also talk about throttling of steam, of non-ideal gases as well, and the same assumption holds that, or I should say, for an ideal gas, it is T2 is equal to T1. For real gases, though, the temperature may not be constant. There may be some temperature changes there. But anyway, no matter what, the throttling process equation is given by delta H is equal to 0. All right. Question is there any real work being done? The answer is no. no real work is being done. So they're asking us to calculate the lost work, and this is what we're doing is we're basically saying, okay, if you take gas from a high pressure to a low pressure just by passing it through a valve, you're actually losing some you're losing some energy, right? You're losing some energy, and that energy can be captured as can be described as lost work. So that's what we're doing. That's what we're doing. So if we go to our equations for lost work, what are they? An equation for lost work we have, I'm trying to find my place in the book. We have a couple different choices. The lost work is equal to the actual work minus ideal work. That's not going to be much help for us. The lost work, the equations that are going to be helpful for us will be, for example, equation 529 or equation 530 to 533. All right, so we can look at, what do you want to look at? Well, either one of those will be fine. If we look at 530, we see that the lost work is equal to m dot. So we're given n dot times T surroundings, right, which we have, times delta S, which is of our gas, minus Q dot. All right, so this is the lost work for this equation. We can immediately say, okay, this is adiabatic. There's no heat transfer between the system and the surroundings. That's equal to 0. Do we know our mass or mole flow rate? Yes, we do. Do we know our T surroundings? Yes, we do. Do we know our delta S of our gas? We don't yet, but I think we can calculate that. If we go back to chapter 5, delta S for an ideal gas, and remember these are state functions, so this applies for every process. Cp natural log T2 over T1 minus R natural log P2 over P1. T2 is equal to T1, so that is equal to 1. That whole thing, log of 1 is 0, right? So delta S is equal to minus R, which is minus 8.314 joules per mole Kelvin, times natural log of 150 kilopascals to 2500 kilopascals. All right, and I get delta S is equal to 23.39. Oops, that's joules per mole Kelvin. And notice I don't care if I didn't change this to a kilopascal unit or whatever, or I didn't change this to bars or anything, because that's just going to cancel. I'm left with joules per mole. And then if I want to, I can multiply that by 20 moles per second. All right, 20 moles per second, and I will get 467.8 joules per Kelvin per second, or that will be watts per Kelvin if you want to leave that, do that. All right, so now we have enough to calculate the lost work. So the lost work is equal to m dot, which is 20, moles per second times 300 Kelvin times 467.8 joules per Kelvin per second. Oops, actually I already included the m dot in here, so let's just get rid of that. I don't need that here because that was already included. So I multiplied through there. Lost work 467 times 300. We do that calculation, that will be 1.4 times 10 to the 5th joules per second, or watts. Either way is fine with me. All right, so that is the lost work that we're doing by throttling this gas. What about the S.gen? Total entropy generation, that's going to be delta S of our system plus delta S of our surroundings. And since we have no heat transfer, there is no heat transfer between our system and our surroundings, there is no entropy change. So delta S.gen is just equal to, you can have it at 467.8 joules per watts per Kelvin, joules per second per Kelvin. All right. And notice that you could, if you had done the calculation like this first, you could have calculated the lost work. This is redundant, but the lost work is also equal to T surroundings times S.gen. That's equation 529, and you will get the same answer. So you're generating lots of entropy, you're losing lots of work with this process.